Okay, in preparation for the unit exam, let's review the unit on fundamental forces. So what are the ways in which matter and energy can interact? Matter and energy interact through four fundamental forces. Matter consists of fundamental particles, but not all particles experience all forces. For example, if I have an electrically neutral particle like a neutron, it's not susceptible to the electromagnetic force, specifically any electric field. The four fundamental forces are gravity, the electromagnetic force, the strong nuclear force, and the weak nuclear force. If I arrange these in ascending order from weakest to strongest, the weakest force by far is gravity, although it doesn't seem that way to us. Gravity is the weakest of the four forces because to generate your weight, it takes your mass plus the entire mass of the Earth, which is considerable just to generate your weight. So the next weakest force is going to be actually the weak nuclear force. Okay, and that's responsible for radioactive decay, amongst other things, alpha and beta decay. The next is the electromagnetic force, which is responsible for electricity and magnetism. And the strongest of all the forces because it can take, the strong nuclear force can take protons and cement them into the nucleus, even though these protons, all having positive charges, want nothing to do with each other. They want to strongly repel each other, but the strong nuclear force can overcome that and keep all those protons tightly bundled in the nucleus. So we have the strong nuclear force is the strongest fundamental force. Next strongest is the electromagnetic force. Second to last in strength is the weak nuclear force, and the weakest force of all is gravity. If I were to trace any force all the way back as far as I could think about it, it would be traceable down to these four. Okay? So all forces and interactions can ultimately be broken down and explained in terms of the four fundamental forces. Matter can be broken down into tiny fundamental subatomic particles which mutually interact through the fundamental forces. Not all fundamental particles experience all of the forces. We mentioned that. And for example, electrically neutral particles like the neutron do not experience the electromagnetic force. What is a plasma? And not blood plasma, obviously, but plasma as a state of matter, a highly energetic state of matter. And how does it compare to other states of matter? A plasma is similar to a very hot gas, but with ionized particles. And what that means is, it means they have a charge when we say ionized. And the way it gets the charge is that it becomes, the gas becomes so energetic that a lot of the electrons that orbit the nucleus of the gas are too highly energized to stay in orbit, and they leave the orbit of the atom, leaving the atom with a positive charge. So this makes the atom a positive ion. And we also have electrons that are roaming around freely. And together, these two constituents make up a plasma. Okay. And a plasma is matter in a state similar to a gas, but in which many of the particles are ionized. And we just talked about that, right? So they're electrons and positive ions. A plasma is matter containing charged particles, positively charged ions, and negatively charged electrons. Notice how we make a positive ion by removing an electron, and we make a negative ion by adding an electron, although we haven't made a negative ion here. So when we charge something, we're always talking about adding or removing electrons. We never deal with the nucleus because that would be a nuclear reaction. That's something else. Plasmas can be created by heating gases until their atoms gain so much energy that they start to lose electrons and become ionized. The temperature of plasmas is much higher than the temperature of gases, liquids, or solids. It's a fourth state of matter. How were the four fundamental forces discovered? Well, the four fundamental forces play different roles in the universe, and their effects show up best in different types of systems. Gravity was the first fundamental force to be understood. It's a long-range attractive force between masses that explains the motion of planets, stars, and galaxies, also close to the Earth's surface. Galileo really investigated gravity first in terms of things falling at the Earth's surface or near the Earth's surface. And Kepler understood gravity in terms of the motions of planets and moons and things like that. And Newton, after a while, put those two things together and came up with a universal, so-called universal gravitational relationship. Electromagnetism provides a unified description of electricity and magnetism. And at one point in the past, people thought that the two phenomena were different. They're actually the same thing. It is an interaction between charged particles and electromagnetic fields that explains electricity, magnetism. Light, yes, light is electromagnetic radiation and forces between charged particles. The weak nuclear force is an interaction between subatomic particles, which is responsible for radioactivity, and the strong nuclear force is an interaction that holds together the protons and neutrons in atomic nuclei, and, by the way, overcomes the strong electromagnetic repulsion between positively charged protons in the nucleus. Currently, researchers use one theory to describe all the forces except gravity. The strong, weak, and electromagnetic forces are described by the theory called the Standard Model. The Standard Model. Gravity is described in the theory called General Relativity. Although we won't go there, we're going to use Newton's somewhat more primitive idea of universal gravitation. That will go something like universal gravitational constant times the product of the masses divided by the distance separating the centers of the masses squared. And we call this an inverse square law, which, by the way, also applies to electricity, where it's called Coulomb's law. So they look very similar, and they'd look even more similar if I didn't forget the square. Okay, so these are both called inverse square laws. What factors determine the magnitude of the gravitational force between two objects? Two massive objects feel an attractive force that can be approximately described by Newton's law of universal gravitation. Okay, that's this guy right here. Or if you can see the really tiny font, courtesy of Discovery Education, you can see that's the same thing. Newton's law gives gives the force F sub g between two masses m1 and m2 separated by a distance r. The gravitational force between them has a magnitude given here. And gravity provides an attractive force. It's only attractive, right? There is no repulsive gravity as far as we know. Gravity provides an attractive force that keeps planets in orbit around the sun. How can atoms and molecules be identified by how they absorb and emit light? Atoms and molecules each absorb and emit only certain wavelengths. Spectroscopy is the study of these properties. Atoms and molecules only absorb and emit particular wavelengths of light. Atoms only absorb or emit photons. A photon is a particle of light. Light can actually be seen as either a particle or a wave. And when we say photon, we're referring to light in discrete packets, separate packets, and that's what a photon means. Atoms only absorb or emit photons of light with energies that match the energy gap between their electron energy levels. So when an electron absorbs energy, when it's orbiting a nucleus and it jumps to a higher orbital, and then subsequently re-emits that energy, it will emit that energy as a photon. Right? So depending where the electron is in orbit, it'll absorb and emit light of certain wavelengths around that atom, and we can tell by spectroscopy, by examining the light that these electrons absorb and emit, what atom that is, or even what molecule that is. The particular pattern of wavelengths that an atom or molecule absorbs or emits can be used to identify the atom or molecule. Atomic spectroscopy is a technique that allows atoms to be identified by the light they absorb or emit. Okay. Any questions about fundamental forces? As if I could answer them now. Okay, since this is a quick review, let's move on to gravity. Okay. How is the magnitude of the gravitational force between two objects related to their masses and the distance between them? The magnitude of gravitational force between two objects is proportional to their masses and inversely proportional to the square of the distance between them. So when I say universal gravitational constant times m1 times m2 over r squared, proportional to their masses, if I double a mass, everybody can see that I double the force. If, on the other hand, let me just get rid of this, and I'll get rid of this. Oop, got rid of too much. Okay, and if I double this, I'm actually going to be dividing that side not by 2 but by 2 squared. You can't leave out the squared, and of course 2 squared is 4. So if I double the distance, I actually quarter the force. And what is Newton's law of universal gravitation? Newton's law of universal gravitation states the following, where well, it's that equation I wrote up there in case you can't see this, where the force is the magnitude of the gravitational force between the two objects. G is Newton's gravitational constant, which is 6.67 times 10 to the minus 11th Newton meters squared per kilogram squared. The gravitational, G is Newton's gravitational constant. The variables m1 and m2 are the masses of the two objects, and r is the distance between them. The gravitational force between two masses is attractive. It is directed along the line that separates the masses' centers. All right, it's measured center to center. So if I have two objects, and this is the center of one, and this is the center of the other, this is the distance between that I use. Okay? What is the difference between center of mass and center of gravity? Well, the center of mass and the center of gravity are related. The center of mass is the average location of the mass in the system, and the center of gravity is the average location of the force of gravity on the system. Typically, these two occur in the same place. When they don't occur is when you have a non-uniform gravitational field. In other words, like for example, if there's large mass a long distance away, like a tidal force from a planet or a moon, there's sometimes enough difference in gravitational field for the center of gravity and the center of mass to be different. Near the surface of the Earth and for small objects, for the most part, they're identical. So they may not be in the same location, but typically they are. Center of mass and center of gravity on an object may lie outside the object's boundaries. For example, if I had something like a horseshoe, okay, the center of mass would probably be someplace in here, along with the center of gravity. So it's actually outside of the object. You could probably say the same thing about a coffee cup. It might have a center of mass someplace, you know, if we were to look inside the coffee cup. Someplace inside. Okay. How does the law of universal gravitation apply to objects near the Earth's surface? Objects near the Earth's surface are acted upon by Earth's gravitational force, which pulls objects downward toward the center of the Earth. It is approximately constant over the range of heights encountered in everyday life and causes a downward acceleration of 9.8 meters per second squared. So if we wanted to figure this out, we had said previously that weight is mass times gravity, but we also said that gravitational force is g m1 m2 over r squared. So near the Earth's surface, we could actually set these two equal. And if m1 is the mass of the object you're considering, then both of these would divide out, and you could actually come up with a number for g that would actually, we're going to say this is the mass of the Earth, radius of the Earth squared. You could actually come up with a number that's going to be really close to this given number of 9.8 meters per second squared. How do we solve problems that involve universal gravitation? You can use Newton's laws of universal gravitation to find the attractive force between two masses. If gravitational force is given, Newton's second law can be used to describe the motion of the object. Motion of the object. How do we use Newton's second law of motion and the law of universal gravitation to solve problems that involve the orbital motions of satellites? The gravitational force between the Earth and a satellite keeps the satellite in orbit around the Earth. If gravitational force on a satellite is given, Newton's second law can be used to determine the motion of the satellite. Okay, so Newton's second law, as we recall, is F equals ma, and F equals g m1 m2 over r squared, where r would be the height of the satellite plus the radius of the Earth, m2 would be the mass of the Earth, and m1 would be the mass of the satellite, which you're probably guessing would divide out. Okay, and would want to use centripetal acceleration here. Okay? But I won't go into a lot of detail about that. Okay, next. Let's look at nuclear forces. Let's see what we see. Let me move me. Okay. What are the strong and weak nuclear forces and how do they work? 4 fundamental forces of nature exist in the universe: gravity, the electromagnetic force, the strong and nuclear force, and the weak nuclear force. The strong nuclear force overcomes the electromagnetic repulsion between protons through the exchange of subatomic particles known as gluons. Okay. The weak nuclear force allows protons to transform into neutrons and the neutrons to transform into protons through the exchange of subatomic particles called W bosons. Physicists use nuclear particle accelerators to study subatomic particle structures and reactions. These reactions allow them to study the behavior of forces and the subatomic particles they affect. How are nuclear fission and nuclear fusion related in terms of mass and energy? Einstein's mass energy equivalence, everybody's heard of this, E equals mc squared, states that energy is equivalent to mass times the square of the speed of light in a vacuum. The equivalence indicates that mass and energy are interchangeable. Nuclear fission is the splitting apart of atoms of heavy elements such as plutonium and uranium. This results in a smaller combined mass of the split atoms, causing some of the energy to be released in the process. Nuclear fusion is the joining together of lighter atoms, resulting in a smaller combined mass and some release of energy in the process. Nuclear fission reactors are reliable and fairly safe sources of energy. Chernobyl comes to mind, so they have to qualify that and say fairly safe, not always. Nuclear fission provides the energy for nuclear weapons, except in the case of a hydrogen bomb instead of an atomic bomb, in which case fusion plays a role as well. Physicists have not yet been able to reproduce the extreme temperatures needed for self-sustaining fusion reactions. They're not talking about bombs here. They're talking about a reactor for generating electricity, like a fission reactor, which is something they've been trying to do for a very long time. What are some examples of technological applications of nuclear processes? Nuclear power plants produce vast amounts of energy with no greenhouse gas emissions. Nuclear weapons resulting from fission reactions are capable of causing enormous devastation to all forms of life. And the medical use of nuclear processes enables technologists to image the human body as well as treat disease using radiation. Okay. And you guys realize that you can go back and retake the quizzes if you think you need additional practice, because those are still open. Also, if you want to get your grades up, you can retake the quizzes and boost your grade. Okay. Let's take a look at electrical forces. How does the electric force relate to the common contact forces people experience each day? An electric force exists between all charged objects. The force arises from charged particles such as the proton and the electron, right? Positive charge, negative charge. Electric forces between charged particles produce contact forces such as friction and the normal force. Like charges repel each other, while unlike charges attract each other. So two positives or two negatives will repel each other, and a positive and a negative or a negative and a positive will attract each other. Atoms, molecules, and entire objects can attract or repel each other based on net charge. So it doesn't need to be all positive or all negative. You could just have a predominance of negative charge or positive charge, and the object would have that net charge. Also, you make a positive charge by removing electrons. You make a negative charge by adding electrons. We don't mess with the protons because that would be a nuclear reaction. Normally, objects are electrically neutral because they contain the same or similar numbers of electrons and protons. However, certain processes such as friction can cause a significant charge imbalance. Right? If you rub one material against another, one object can actually, charging by friction, can actually pick up electrons as another one loses. Right? The one that picks up electrons will have a negative charge. The one that loses electrons will have a positive charge. On an atomic level, forces commonly referred to as contact forces are actually not in contact. Rather, the electrons from one object repel the electrons in another object at a distance. For instance, when a book is set on a table, the outermost electrons in the table repel the outermost electrons in the book. This produces a normal force that supports the book. However, it does so without any particles in either substance coming into contact with one another. Right? The fields of each repel one another. What determines the strength of an electric force? Coulomb's law governs the strength of the electric force between two charged objects. Coulomb's law states that the electric force is determined by the amount of charge on the two objects and the amount of distance between them. In fact, Coulomb's law looks a lot like Newton's law of universal gravitation, where Q1 and Q2 are charges, like M1 and M2 were masses, where K is a constant, like capital G was the universal gravitational constant, and R is the distance between the two charges, specifically the distance between their centers. The electric force is directly proportional to the product of the charges. The greater the charges, the greater the force between the two objects. Okay, so it's akin to mass in Newton's universal gravitation equation. Electric force is inversely proportional to the distance between the two objects. Actually, it's inversely proportional to the square of the distance between the two objects. The greater the distance between the two objects, the smaller the force between the two objects, right? If they're further away, obviously they have less influence on each other. And if two objects have like charges, the electric force is repulsive. Okay, so this is a little different than gravity. Gravity is only attractive. With electrical charges, it could be repulsive if the charges are alike. And if the two are unlike, then it's like gravity in that sense. The force is attractive. Okay? Hope everybody has, hope that clears up, or at least gives everybody a fast review for electric forces. Don't forget, you can log into Discovery Ed and retake or reread from either the quizzes or from the online textbook, the tech book, quote unquote, and redo any of this material. Okay, so this is designed just to be a quick review. Okay, forging ahead. Centripetal force and circular motion. So, how can problems related to centripetal acceleration and uniform circular motion be solved? Well, let's talk about what that means. If I have an object and it rotates about some center, let's say it's attached to a string and at the center is my hand and it's, whipping it around into a circular path over my head. Right, I'm looking down at this object traveling in a circle. What centripetal means is center seeking. So the force and the acceleration both go to the center. So centripetal means center seeking. It's always seeking the center. Okay, so the centripetal force is pulling this object to the center, and its instantaneous or tangential velocity is always at right angles to the centripetal force and the acceleration, so that the speed never changes, but the direction does constantly, because remember, velocity is made up of two things. It's made up of speed plus direction. So when something goes in a circle, there's not only a centripetal force and acceleration acting, but it also means that the velocity and that centripetal force and acceleration act at right angles to each other, right? It doesn't speed it up, it doesn't slow it down, it just keeps changing its direction. That's the formula for centripetal acceleration. Let me rewrite that. Okay, so v sub t is the tangential velocity. It's squared, and you divide that by the radius of this circular path, right, which would be this distance in here. Okay. What are the force and acceleration vectors that are involved in centripetal acceleration? Centripetal force directed toward the center of the circle. Remember, centripetal center seeking acts on a moving object to provide centripetal acceleration and to keep it on a circular path. It does this by providing a net force to the center of the circular path that keeps nudging its direction without changing its speed. So centripetal force can be provided by gravity, friction, and/or tension. It can also arise for other reasons. Could be normal force, like when the clothes are on spin cycle inside the drum in the washing machine. That normal force keeps pushing the clothes to the center. And at the same time, the holes in the drum don't push on the water. So this has the effect of separating the water from the clothes. If you've ever seen a salad dryer, okay, same idea. You can have electromagnetic forces that act centripetally on charged particles. All kinds of things. Okay, so when we say a centripetal force, it's not a particular force, or how discovery education would imply that it's a fundamental force. Far from it. It just tells you which way the force points. It points to the center, okay? And that force could arise from gravity, friction, tension, electromagnetism, all kinds of forces, okay? And centripetal force is actually centripetal acceleration brought into the second law. So if net force is mass times acceleration, and centripetal acceleration is v squared over r, then centripetal force is mv squared over r. Okay, so that's where they get that from. And how do centripetal and tangential accelerations differ? We're only going to deal with uniformly accelerated motion. We're not going to deal with tangential accelerations, that is, in addition to a continually changing direction, consider a continually changing speed as well. Something going in a circle and speeding up or slowing down. But if there was a tangential acceleration, it would mean that something is going in a circle and is speeding up or slowing down. So the centripetal acceleration vector points toward the center of the circle. Centripetal acceleration acts to change the direction of the object's velocity vector, and the tangential acceleration acts along a line tangent to the circular path. Tangential acceleration acts to change the magnitude of the object's velocity vector. Okay, so I drew this before. You have something going in a circle, right? Centripetal force and acceleration go that way, and the tangential velocity, if this is going around clockwise, will go in this direction, right? If you take a look at it a little while later, well, the force is still tangential, and centripetal, and the velocity is tangential. Okay, so the force is still pointing to the center, the acceleration still points to the center, and the velocity is tangent to the circle. Okay. Okay, there's a Ferris wheel, all kinds of good stuff. Okay, last one. Last one. Okay, work and power. We went up and down the stairs a little bit with this to illustrate the point. Work is force times distance. So if something is sailing along through space, but there's no force acting on it, that is to say it's sailing along through space at a constant speed, no work is done. By the same token, if I apply a great force to something, and that thing experiences no displacement, it does not move in any direction, no work is done. Okay? So anything times zero is zero. So you must have a force, and that force must move the object through a displacement. If it's off axis, okay, say this is the force and it's displaced in this direction, then the work would be force times distance times the cosine of the included angle. Okay? So just make a mental note of that someplace. For the most part, we're just going to say it's force times distance because we're going to assume that the force is happening in the direction the object is moving. So work is done when a force or a component of the force acts on an object in the direction of its displacement. Work is not done when there is no motion. Similarly, when there is motion but there's no net force, work is also not done. For a constant force acting at an angle to the direction of the motion, the general formula for work is force times distance times the cosine of the angle between the force and the displacement vectors, where theta is the angle between the force and the displacement vectors. The general formula for work shows that work is not done by a force that is perpendicular to the direction of the motion. Obviously, the cosine of theta at 90 degrees is 0. So that's another case where no work would be done, where force and displacement are at right angles to each other. The general formula for work shows that the work done by the force is greatest when the force and the displacement are parallel. Work is a scalar quantity. It can come with signs, but it does not indicate direction. Instead, it indicates if you're adding energy to something or taking it away from something. We call energy work when we're adding it to something or taking it away. Okay, so work really is energy, and it has the same units, joules. And it's equivalent to a Newton meter, or a Newton times meters. Work is the transfer of energy. Okay, work is energy in transition. So the average power Okay. So if work is energy, then power is actually the work done per unit time. Okay? So if I were to plot work as a function of time, the slope of that line would be the power. Okay? How are power problems solved? The average power delivered per unit time is given by this formula. Oh, I just gave it up here. And power is the rate at which work is performed, and the unit for power is the watt. You guys might have seen this on the top of light bulbs. Maybe it says something like, I don't know, 60 W. That's 60 watts. And a watt is 1 joule delivered, 1 joule of energy delivered per second. Okay, so notice in our little experiment running up and down the stairs that your weight in newtons times the height of the stairs gave you the work, and of course that didn't change in our 2 trials. That remained the same. It was the same amount of energy. The stairs didn't change height, and of course you guys didn't change weight as you ran up the stairs, not significantly anyway. But when we looked at the 2 different times we got and we divided that by the work, we found that a short time dividing by a small number gives us a larger result, gives us a higher power than if we just took a leisurely walk up the steps, and that would have represented a smaller amount of power. Okay? So I hope that is understandable, and everybody can take a look at this, and it helps you study for the exam. Remember, you can always go online, take a look at previous quizzes, and read the chapters in the textbook. Okay.